So let us conclude our discussion of the problems of numerical algorithms by looking at a case study. So this case study involves computing the roots of a quadratic. Right? So we know that the roots of a quadratic, so if I have an equation of some ax squared plus bx plus c, then the roots can be obtained by solving this following equation. So the first root is minus b plus root of b squared minus 4ac divided by 2a, and the second root is the same thing but minus, right? So this is a standard formula for finding the roots of a quadratic equation. So the first problem is, how do you compute the square root? So the first problem with this formula for square roots is, how do we actually compute square root of d, right? So there's a very elegant algorithm due to Newton. So it's an iterative algorithm. So you start off by estimating that your value that you want. Remember that we are solving square root of a capital D. So you start with the concrete value 1 plus d by 2. Right? And at each stage now you'll compute x of n plus 1 as the value x of n plus d upon x of n, the whole by 2. And you can actually show that this thing will converge pretty rapidly. In fact, if d is in the range, for example, 1/4 to 1, then in 4 iterations, the error is within 10 to the minus 15. Now, of course, this is an iterative thing, so you have to know when to stop. So stopping, you have two options. So either you can compare xn and you can, okay, so if the difference between xn and x1 plus 1 is less than some threshold, then you know that the value is not changing by much and you can stop. Or you can look at actually d minus xn plus 1 squared. So this is your current value for the square root. So if you square it and you subtract it from d, and then you check whether this is below some threshold. So either of these two things. So what you can show is that if you have d in this value, then the difference between d and this nth computation after 4 iterations is less than 10 to the minus 15. Right? So we have a fairly decent way in which to compute square roots. So we can see how to compute square root of 2 using this method, for example. So x0 is going to be 1 plus, so in this case remember d is 2, so 1 plus 2 divided by 2, that's going to be 1.5. So this is our first estimate. Now x1 is going to be 1.5 plus 2 divided by 1.5, the whole divided by 2. Right? And this turns out already to be 1.416667. And now if you do the same thing with x2, you take x2 to be x1 plus 2 divided by x1 upon 2, you'll get 1.414216. You can work it out with the calculator and see. If you take x3 is going to be now x2 plus 2 by x2 divided by 2, you'll get 1.414214. And now if you take the fourth approximation, so you take x3 plus 2 by x3 divided by 2, we'll actually get 1.414214 again. And so now you can see that this thing is not changing up to single precision 7 digits, so you'll stop and you'll get this estimate. So it's a very rapid convergence that Newton's algorithm gives you for the square root problem. So we know how to compute square root of d. So is this enough to compute this formula for the roots of a quadratic? Right? So is this the only obstacle that we have? And the problem is, it's not the only obstacle, and because the problem we face here is again our old foe, which is subtractive cancellation. So here the difficulty is that in the numerator we have things which are of opposite sign. So if b is greater than 0, okay, then we have the problem that x1 involves minus b plus b squared minus 4ac. So this is a positive number, so minus b is negative. So now the numerator has cancellation. So I have a cancellation possibility here. And then likewise, if b happens to be less than 0, x0, x2 numerator has subtractive cancellation. Because now what happens is that if b is greater than 0, then this is a positive, this is a negative number. So minus b becomes a positive number. And then we are going to subtract this discriminant. And so we are going to get, again, some subtractive cancellation. So here is a particularly bad example to illustrate this. So if you take x squared minus 10 to the 5x plus 1 equal to 0 as your quadratic, then in this case the real x1 star happens to be 99999.9999990, and the real x2 star is a very small number. It's something like this. Right, so x1 star is almost 10 to the power 5, 10 to the power 5, yes, and this thing is almost 0. So now in this case what happens is, if you use that naive discriminant formula to compute, so if you compute minus b plus minus b squared minus 4ac by 2a, then what you'll end up with is computing x1 to be this number, and you compute x2 to be 0. Okay? So x1, this is not a bad number to get, but this is definitely not an acceptable thing, because you don't want to truncate this thing to 0. Right? So what can we do in this case? So as we said before, one of the solutions to deal with this underflow overflow problem is to change the value that you compute from the original formula to a rewritten formula. So let's look at this example with x1. So x1 is minus b plus the root of b squared minus 4ac divided by 2a. Right? Now supposing I take the numerator and denominator and multiply it by minus b squared minus 4ac divided by minus b squared minus 4ac. Right? So I'm just multiplying by 1 in some sense. Now this is of the form x plus y, x minus y, so this becomes x squared minus y squared. So I'll end up at the top getting b squared minus b squared plus 4ac. Right? So I'm going to end up in the top getting b squared minus b squared plus 4ac. And at the bottom I have 2a and then this green term. So the b squared will cancel, this will cancel, right? And so what I end up with is 2c upon minus b squared minus 4ac. Now what is the advantage here? Well, remember that x1 had a problem if b was positive. If b was positive, minus b plus this thing was a subtractive thing, but now minus b minus something, so it's become a 2 negative, so it's become an additive thing. So I've eliminated the subtractive cancellation problem for x1, and for x2 I can use the original formula, because there is no subtraction. So this is the case if b happens to be bigger than 0. So if b happens to be bigger than 0 for x1, I rewrite the thing so that I subtract a negative from a negative, so I get 2 negatives and there's no subtractive cancellation. And x2, there's no subtractive cancellation anyway in the original formula, because this is negative, so minus b is plus, sorry, this is positive, so then you will end up with minus b minus something, so there's no problem. And on the other hand, you do a symmetric thing. So if b is less than 0, then x1 there's no problem. In other words, you just use minus p plus b squared minus 4ac by 2a, right? Because this is negative, so minus b is positive, so this is just an addition. But for x2 you do a similar trick and you will end up computing x2 is now 2c. You do the same trick as before and you work it out, and you will get 2c by minus b plus b squared minus 4ac. And now since b is negative, minus b is positive, so again the subtractive cancellation is disappeared. Right? So by doing a suitable rewriting, we have eliminated both subtractive cancellations, and this allows us to compute the roots of a quadratic equation using Newton's formula for the square root without having any subtractive cancellation. So to summarize, so numerical computations require careful analysis of errors. So these are errors which could arise because of finite approximations of infinite objects, and these are called truncation errors because you're only computing part of the quantity, or because of the bounded representation in terms of mantissa and exponent. You can have round off errors, and this can lead to overflow or underflow. And then if you compare and subtract two numbers which are very close to each other, then the relative error can get magnified. So you have this problem of subtractive cancellation. And in some cases, when this error propagates from one stage to the next, the inputs to the next problem may change slightly, and if the outputs are perturbed badly because of the inputs changing slightly, then you have what is called an ill-conditioned problem, and this could lead to major instability in the computation you're trying to achieve.